Hello everyone, my name is Surya Raghuvanshi and I am here to explain Kruskal's algorithm and how it is used to generate minimum spanning tree. Before we understand Kruskal's algorithm, we must first understand what is a spanning tree and a minimum spanning tree. The subgraph of an undirected connected graph is a spanning tree. It has all its vertices as well as fewest amount of edges feasible. It is not a spanning tree if any vertex is missing. A spanning tree is a subset of a graph that has no cycle and cannot be joined. For a weighted connected undirected graph, a minimum spanning tree or MST is a spanning tree with a weight less than or equal to the weight of every other spanning tree. Weight of a spanning tree is the total of the weight assigned to each of its edges. Now, when we need to find the number of edges of a minimum spanning tree, we just subtract 1 from number of vertices. So for a linked weighted graph, Kruskal's algorithm is used to discover the smallest spanning tree. The algorithm's main goal is to locate subset of edges that may be used to visit every vertex of the graph. Instead of focusing on a global optimum, it uses a greedy method to discover an optimal solution for each step. Now the question arises, how is an MS tree generated with Kruskal's algorithm? We just need to follow some basic steps. Step 1, sort all the edges from low weight to high weight. Now, step 2 will be to pick the edges with the lowest weight and add it to the spanning tree. One note that we need to keep in mind is that if the edge is creating a cycle, we need to cancel that edge uh, uh, and continue till all the vertices are connected. Now let's see this with the help of an example. Consider the following figure. There are 9 vertices, so the smallest spanning tree will have 9 minus 1 is equals to 8 edges. Now we have to arrange the data set. First, the original data set would look something like this, like the figure which we have shown, the unsorted edges. And the sorted edges would look something like the second figure. Here, S is the start, E is the end, and W is the weight. Now we need to pick each of the edges one by one. When we pick the edge which connects 6 to 7, we see no cycle here, so we include it. Now, next we see the edge 8 and 2. Still there is no cycle formed, so we include it as well. Next we will see edge 6 and 5. Still no cycle is formed, so we include it as well. And so on, we'll go to the next edge, that is 0 and 1, and we still don't see any cycle. The next edge will be 2 to 5. Still no cycle is formed, so we will include it as well. Now, when we go to the edge 8 to 6, this side will make a cycle, so we are not going to include this side. Next, we'll go to the edge 2 and 3. No cycle is formed as well, so we are going to include it. Next, we'll go to the edge 7 to 8. This side will make a cycle as well, so we are not going to include it. Now, next will be the from edge 0 to 7. This does not form a cycle, so we are going to include this. Now we pick the edge 1 and 2, and this will form a cycle. So we are not going to include this side. At last, we'll pick edge 3 to 4, which will connect us to the last edge, and it will not form a cycle, so we are going to include it. This will be our minimum spanning tree. This will be our minimum spanning tree as it has 9 minus 1, 8 edges, and all vertices are connected without forming a circle. Here we have created a spanning tree with the help of Kruskal's algorithm. Now let us try to understand the time complexity of Kruskal's algorithm. Here we have created, as you can see, in the second figure, initializing the set A in the line 1 takes time O bracket 1 time. The time to sort the edge in the line 4 is O bracket E log E. In line 5 to 8, for the loop performs OE find sets and union operation on the disjoint set forest. Along with modulus of V make set operation, these utilize a total of O bracket V plus E alpha V time. Since we assume that G is connected, we have E less than V minus 1. So the disjoint set operation takes O E alpha V time. Moreover, since alpha V is equals to O log V is equals to O log E, the total running time of Kruskal's algorithm is O bracket E log E. Observing that E is less than V ki power 2, we have the log E is equals to O log V. And so we can restate the running time of Kruskal's algorithm as O E log V. That will be all from my side. Thank you for watching this video.